Hello, I hope everyone is doing well. My name is Gisselle Sainz, and my proposal topic is on carbon and oxygen isotopes and how they can be used to determine the cause of the Permian-Triassic extinction. My presentation will essentially follow the NSF Graduate Fellowship application format, starting off with an introduction to give some necessary background information, then followed by my proposed research and method to test my hypothesis, and finally end with the intellectual merits and broader impacts of my topic. So, first of all, the Permian-Triassic extinction was an event that occurred about 202 million years ago. It wiped out about 93% of all living organisms on Earth, and this in turn led to massive rediversification of all remaining organisms. Now, unlike our historical understanding of the Cretaceous Paleogene extinction, where a meteor impact led to the death of the dinosaurs, the cause of the Permian-Triassic extinction is less clear. Most of it is highly speculated given that it occurred much longer ago than the extinction of the dinosaurs. Although we are not scientifically certain of the cause of this extinction, there is a theory that it occurred as a result of an abrupt climate warming event that followed after a massive volcanic eruption within the Siberian Traps. So, to explain further, the volcanic eruptions may have released enough carbon dioxide into the atmosphere to exacerbate the greenhouse gas effect, and as a result, global temperatures may have increased to a point where most organisms on Earth could not adapt to it, and so they didn't survive. So, how do we test this theory? Well, isotopic delta values within rock samples can be used to track any geochemical shift throughout history. So, in this case, I want to focus on carbon and oxygen isotopes. The reason why is that carbon isotopes can tell us where carbon dioxide came from during specific time periods. Carbon-12 tells us if it came from photosynthesis or fossil fuels, although during the Triassic period that's highly unlikely. And carbon-13 tells us if carbon dioxide in the sample came from a volcano, which would support the theory. Oxygen isotopes, on the other hand, are also useful for testing this theory because it gives insight about the temperature of the Earth throughout history. And this is because of oxygen-16's presence in polar ice masses. So, to explain, due to the latitude effects, when air masses are moving to higher and cooler latitudes, it tends to precipitate oxygen-18 first because it is a heavier isotope. Hence, by the time these air masses reach the poles of the Earth, they are completely depleted of oxygen-18 and are only left with oxygen-16. And ultimately, this is why ice masses accumulate oxygen-16 instead of oxygen-18. So during a warming event, ice bodies will melt and release oxygen-16 into the ocean, and during a cooling event, ice bodies will grow and accumulate more of this isotope from the ocean. And here we can see how isotopic ratios from samples are used to calculate delta values. Delta values are expressed in per mil, and the standard is an established reference material. Judging from what we know about the behavior and origin of carbon and oxygen isotope ratios, in order for a sample to support the volcanism and global warming theory, it must display an increase in delta carbon-13 and a decrease in delta oxygen-18. Similar research on this topic has been performed on the South China Block, specifically in the Jingye section, and in the northern Indian margin, specifically in the Lozar section. The isotopic composition within these rocks have supported the theory that the Permian-Triassic extinction was the result of a spontaneous climate change event induced by a major volcanic explosion in Russia. The samples within the previous study showed how delta carbon-13 rapidly increased, then gradually decreased, and rapidly increased again, and on the contrary, delta oxygen-18 decreases, increases, and decreases again. This image demonstrates the 3 shifts in carbon isotopes, where here we see that it increases, and then it decreases, and then it increases again in both the Lozar and the Jinya sections. So this suggests 2 things. First, the occurrence of 2 major warming events with a restoration phase in between, and second, the fact that isotopic fluctuations occurred over a broad distance, at least from China to India. However, it is important to recognize that the current location of countries is not the same as it was during the Triassic period due to continental drift. In my personal research, I want to extend this distance further to reinforce how this volcanism and climate change theory could have been responsible for an extinction occurring at a global scale. On this map from the Triassic period, we can see where China and India were located, and I personally want to go further and test rock samples from the United States. So you can see here, North China, South China, and then India, and then North America would be extending this distance a bit further. So I want to focus on the Moyonkopi and Shinnerup Formation within the US. My goal is to replicate the previous study's method of sample extraction and isotopic analysis in order to verify whether the results are relatively reproducible. If my results coincide with the results of the previous study, then the volcanism and climate warming theory is supported. If not, then my results reject this theory or an unaccounted error occurred within my analysis. So here's some background information on the Moyonkopi and Shinnerup formations. Moyonkopi is composed of sandstone and it formed during the Triassic period, and Shinnerup is made up of sandstone and conglomerate, and it was also deposited during the Triassic period, and this makes both of the rock formations suitable for testing this theory. And as you can see here, I drew the relative locations of both of the formations, and red and cyan, red being the Moyonkopi formation, and cyan being the Shinnerup formation. The method I plan to use to find my delta values is mass spectrometry. Mass spectrometry separates isotopes based on their mass, making it easy to find the isotopic ratios of our sample to plug into the delta equations shown again on the right. I would like to collect 20 to 30 samples from both formations and drill them into a fine powder before inputting them into the spectrometer. For more accuracy, I plan to repeat this process twice with a new set of samples and compare my results from both trials. Depending on whether or not my results coincide with the previous studies conducted by different scientists, the hypothesis about the cause of the Permian-Triassic extinction will either be supported or rejected. My research will primarily be used to verify or contradict how isotopic fluctuations happened across a distance that extends even farther than between China and India, in terms of where these countries were geographically located during the Triassic period. In addition, my study will help to improve the scientific understanding of the Permian-Triassic extinction by addressing the effects of geochemical shifts on biotic survival and well-being. Lastly, my research will help explain the evolutionary development of current life on Earth and how this current life has adapted alongside geochemical progressions within our global environment. For now, I plan to present my research to my fellow classmates in this geochemistry course. Afterward, if the interest arises, I would be willing to publish my results and interpretation of them within an academic paper where my work can be further revised and debated amongst the worldwide community of geochemists. Once my work has been revised, I aim to share my research at conferences where my discoveries can be further spread to other scientists, students, and curious minds. And so this concludes my presentation. Thank you all for clicking on this to listen. If anyone has any questions, please feel free to post it and tag me on Questionsly. Thank you.